Hi, my name is Ken Kreider, and in this video we're going to talk about exponential growth and decay. The objective of this lesson is that students will be able to solve problems involving exponential growth and decay. Let's take a look first at the exponential growth model. The equation is y equals a times 1 plus r to the t power. In this equation, y represents the new amount or population, a represents the start amount or population, r represents the growth rate, and t represents the number of time intervals. Bacteria often follow the model of exponential growth as they multiply. When you graph exponential growth, you tend to get a curve that looks something like this. As you can see, it's curving sharply upward. As time passes, the population size is increasing dramatically. Let's take a look at an example involving exponential growth. A fish hatchery contains 9,000 fish. The fish population is growing at the rate of 5% per week. How many fish will there be after 30 weeks? This problem involves exponential growth. Why? Because we can see that the population is increasing. So we will use the exponential growth model. We need to replace A with the starting population, 9,000. We also need to convert the growth rate R, or 5%, to a decimal, 0.05. The number of time intervals T is 30. So let's plug in our numbers, and then we can do the math. As you can see, we've replaced A with 9,000, we've replaced R with 0.05, and we've replaced T with 30. To simplify this, we need to use the order of operations. So we're going to add the 1 and the 0.05 first, since that's inside the parentheses. And of course, that's 1.05. Now, we need to do the exponents next before we multiply. So we need to take 1.05 to the 30th power before we multiply. 1.05 to the 30th power is 4.3219. Now let's multiply that by 9,000, and we get 38,898 fish. As you can see, I've rounded this off to a whole number because fish come in whole numbers. This is a population. Whether it be fish or people, whenever there's a population, you want to use whole numbers. We don't want to talk about half a fish or something like that. Now let's take a look at the exponential decay model. Y equals a times 1 minus r to the t power. The only difference between this equation and the one for growth is that we have a minus sign in the middle here instead of a plus sign. The variables are very similar and represent pretty much the same thing. Y represents the new amount or population, A represents the start amount or population, R represents the decay rate this time. We're calling it the decay rate instead of the growth rate this time, and T represents the number of time intervals. When you graph decay, you tend to get a curve that turns sharply downward, like this one, and it slides out at the bottom, kind of flat at the bottom. Let's take a look at an example involving exponential decay. The car is purchased for $30,000. The value of the car depreciates at the rate of 15% per year. How much is the car worth after 3 years? This problem involves exponential decay. Why? Because we know that the value of the car is going down. So we will use the exponential decay model. This car value is going down, and that's depreciation. So here's the decay model. Let's replace our variables. The start amount was 30,000. That's going to replace the variable A. We're going to convert our decay rate, R, 15% to a decimal. As a decimal, that's 0.15. We simply move our decimal point 2 places back. In a whole number, the decimal point is after the last digit. So if we move it 2 places back, it's going to land right before the 1. The number of time intervals, T, is 3 years. Now let's plug in our numbers. A is replaced by 30,000. We replace R with 0.15, and we replace T with 3. Again, we need to start inside the parentheses using the order of operations. As we simplify this, 1 minus 0.15 is 0.85. And now we're going to take 0.85 to the third power first before we multiply. 0.85 to the third power is 0.614125. Let's multiply that now by 30,000, and we'll get this number, 18,423.75. This time we'll keep a couple of digits after the decimal point, since this is money, and those two digits will represent the cents. So this car has depreciated for 3 years, and we expect the value to be $18,423.75 after 3 years, since it has depreciated at the rate of 15% per year. In summary, we've been talking about two different equations, but they're very similar. One for exponential growth with a plus sign in the middle, and one for exponential decay with a minus sign in the middle. In both equations, y represented the new amount, a represented the start amount, r represented the growth or decay rate, and t represented the number of time intervals. It's important to note that when the rate is given as a percent, you need to be sure and convert it to a decimal first before replacing r in the appropriate equation. I hope you've enjoyed this lesson on exponential growth and decay, and I'll see you next time.